Hey everybody, this is Mr. Beckstrom, and today I wanted to do a review of the SLO quiz that's going to be due pretty soon here. So let's go ahead and take a look at some examples here. So these will be pretty similar to the ones on the quiz. It's really important that you understand how to do these. So the first one says, what is the tangent of pi over 3? Well, if we remember, the tangent is defined as sine over cosine, so I can look at the sine of pi over 3 over the cosine of pi over 3, pi over 3, and this is going to be equal to, well, I need to know what these two are. Remember, the sine relates to the y coordinate at this angle, and the cosine relates to the x coordinate at this angle here. So if I go ahead and pull up this, and I look at pi over 3, the y value is the square root of 3 over 2, so that's the sine of pi over 3, and the x value is 1/2, so that's the cosine. So that's what I'm going to do here. I'm going to do the sine, which is square root of 3 over 2 divided by 1/2. And then I can multiply the top by the reciprocal of the bottom, so 2 over 1. The 2's will cancel out, and I am left with just the square root of 3 over 1, which is the square root of 3. And that would be my answer. Now, if I try to do this in my calculator here, making sure that I was in radians, which I am. Let me change this back to function here. If I were to just put in the tangent of pi over 3, tangent of second pi divided by 3, it's going to give me a decimal number here. And there's no way for me to have the calculator convert that to a square root. But this is equal or approximately equal to the square root of 3, and I can verify that just by going second square root 3, enter, and see that they're both the same decimal approximations. So this is a good way to check my answer. Just take my answer and put it in both of these ways, and you should be able to make sure that that's correct. Alright, the next one is the cotangent of pi over 3. So we're basically going to do the same thing, except this time I'm going to do the cosine of pi over 3 over the sine of pi over 3 because the cotangent is just a reciprocal function of the tangent function, so you just reverse these. So that's going to be, we already looked those up, so now this is going to be 1/2 over root 3 over 2. So I can multiply the top by the reciprocal of the bottom there. 2's cancel out, and now I'm left with 1 over root 3. And I want to check that in my calculator again. So I'm going to do the cotangent. Now remember, the normal TI-83, TI-84 calculators don't have cotangent, but since it's a reciprocal, I can write it as 1 over the tangent. So that's what I'm going to do here. I'm going to do 1 divided by the tangent of pi over 3, so second pi divided by 3, and this will be the same as the cotangent as long as the denominator is not equal to 0. So this is what I get. Now let's see if that's equivalent to 1 over root 3. So I'm just going to put 1 divided by square root of 3, and sure it is. It sure is. So this is a good answer here. The next one is the cosecant of negative 1/2. And remember, the cosecant is equal to 1 over the sine. The cosecant and the sine are related. They're reciprocal functions of each other. So I can write this, I'm going to do it over here, give myself a little bit of space. I can write this as 1 over sine of 1/2. Oh, hold on just a minute. This is not an angle, that is a value there. I think this is meant to be the inverse cosecant. Alright, so actually this 1 is supposed to be a pi here, so I'm going to change that to pi. Because if we just did negative 1/2, that wouldn't make sense. So this is not a inverse function. It is just the topic here is negative pi over 2. So if we had the 1/2 in here, it wouldn't make sense because this should always be an angle inside there. Now it technically could be 1/2. Then we would put that in as a radian, but this isn't what I meant to do here. So we can write this as the 1 over the sine of negative pi over 2. Then we have to know what the sine of negative pi over 2 is. We can do that a couple of different ways. I'm just going to go here to my unit circle here, and starting at 0, this is positive pi over 2, so negative pi over 2 would be just the same distance in the opposite direction, and that's going to be 3 pi over 2. And the sine of 3 pi over 2 is negative 1. The sine of 3 pi over 2 is negative 1, so I come back here, and I'm going to do over negative 1. So 1 divided by negative 1 is just negative 1. So that should be my answer. And let's go ahead and check that in the calculator here. So we're going to do 1 divided by the sine of negative pi over 2. So negative pi divided by 2. And I should get a negative 1, which I do. So that one looks good. Another way I can do this is also find the angle in the standard position. That's the one between 0 and 2 pi. And I can do this by adding 2 pi to this angle here. So if I take negative pi over 2, and I'm just going to write it as negative 1/2. Maybe that's why I messed up in the beginning. And I add 2 pi, which I'm just going to add 2. I'm just going to leave the pi's off and then put them back at the end. That gives me 1.5. Convert that to a fraction, and that's 3 over 2. And you put the pi back in, that becomes 3 pi over 2. So we can also just add any multiple of 2 pi to that angle, and it's going to be an angle going in the same direction. And by adding one of those 2 pi's, that gets us in the standard position so we can see it on our unit circle. All right, determine the period and the range of 2 secant x over 2 plus 1 minus 5. Now this one looks pretty hard, but it's really not too bad. So we'll start with the period. So the period of the normal secant function is equal to 2 pi. And in this case, all we're going to do is we're going to take that 2 pi and we're going to divide by whatever coefficient or whatever scalar or constant is multiplying the x here. And really, I'm going to do this off to the side, x over 2 can be written as 1/2 x, right? These are the same things, and then I can easily see that the number I'm multiplying the x by is 1/2. So to find the period here, I'm just going to divide that 2 pi by 1/2, and that's going to end up giving me 4 pi. I can multiply by the reciprocal of the denominator, which the reciprocal of the denominator is 2, so 2 pi times 2 is equal to 4 pi, and that will be my period. So that's the distance which it takes for this function to start repeating. Now the range, the normal range of a secant function is negative infinity to negative 1, including negative 1, and then positive 1 to positive infinity. And this is in the notation that they had asked for, interval notation. So how do we see what the range is here? Well, the 2 out here is going to amplify it. Basically, you multiply this negative 1 here and this positive 1 by 2. So that brings it to negative pi to negative 2. And running out of room here. Let me, and 2 to infinity. So first we're going to take a look to see what this 2 out front here does. That multiplies both of these values here. And then the minus 5 on the end, then we're going to subtract 5 from those 2 values as well, because it's going to shift the entire graph down by 5 units. So our final answer for this will be negative infinity to negative 2 minus 5 is negative 7. remember, bracket here, and then the join symbol, which use the symbol that's offered as one of the buttons at the bottom of the screen. And then 2 minus 5 is -3, all out to, excuse my bad writing here, but this should be your final range here. And we can verify that if we want to. What I can do here is, let's go to my y equals, and I'm going to put in that function there. So 2 times, now this is tricky, we don't have secant, so we can write that as 1 over cosine, because secant and cosine are reciprocal functions of each other. And I'm going to put the whole thing in parentheses. 1 divided by the cosine of x over 2 of x divided by 2 plus 1, and make sure you close the parentheses for that, and then we're going to do minus 5. So this here should work and kind of let us visually see what that range is as well. And zoom, let's try a standard. And as we can see here, if we use the trace function, there's nothing between this point and that point as far as the y values. So if we look at, oops, can I change? Oh yeah, let's go this way here. So we can see the highest y value coming up from -infinity is right at -5 there. You can see that y value. And then it comes back to -1 here, the y value -1 right at the bottom there, and goes up to positive infinity. So we can see it that way as well. And we can also kind of check our period, because it'll be from the center of this point to the center of that point. So I can look at those two x values, find the difference between those two, and verify that that's going to be right at 4 pi. All right, now for number 5, we have the angle of elevation to the top of a tower from point A on the ground is 13.7 degrees. From point B, it's 23.3 feet closer to the tower. The angle of elevation is 15.2 degrees. What is the height of the tower? All right, so what we're going to do here, I'm going to give myself a little bit more room, is I'm going to go ahead and draw this out. So we have, okay, and we're going to, oops, keep messing with that. All right, so do. Oh, it didn't go to shape here. Ink to shape. All right, let's try that again. So there we go. All right. So what is an angle of elevation? An angle of elevation is the angle from a horizontal line going up. So if this is the height of the tower here, and let's kind of make this like into a tower, right? Little windows there, horrible looking tower, right? And we want to know the height of this tower, the angle of elevation from some point A on the ground. That's given to us as 13.7 degrees. And then we go in 23.3 feet closer, 23.3 feet closer. And then our new angle of elevation, and let me use a nice little ruler for this. Our new angle of elevation is, and let me close that out, 15.2 degrees. So from this point, 23.3 feet in, it's now 15.2 degrees. Up to the top of there. So the question is, how do we find this height here? So what I'm thinking is we have a right triangle here, so we can use the trig functions. And from this angle here, this is going to be the opposite side, right? So I'm going to need to use one of the trig functions that uses the opposite side, which is either sine or tangent, using SOHCAHTOA. But I don't have another side. I don't have this side here, and I don't have this side here. So how can I find one of those sides in order to kind of complete that formula there? And the answer is, even though this is not a right triangle here, this kind of obtuse triangle, we do know that law of sines works for any triangle. And law of sines says that the sine of an angle over its opposite side is equal to the sine of another angle over its opposite side. And so that's what we're going to use here in order to find this length of the hypotenuse of the smaller right triangle. Alright, so let's go ahead and do another ink to shape here. And first I'm going to look at this kind of obtuse triangle here. And it's going to be something like this, right? There we go. And then finally after that I'm going to be looking at that right triangle. I'll go ahead and write that in there. So we have that as well. Alright. So for this one here, I know this is 23.3 feet. I know this angle here is 13.7. Oops. 13.7 degrees. But I don't know the other two angles yet. But I know that going from here to here, that's a straight line. So that's 180 degrees. So if this is 15.2 degrees, then this one here has to be 180 minus 15.2. So that's what I'm going to do here. I'm going to do 180 minus 15.2. And I get 164.8. Alright, 164.8. And sorry about that. And then the final angle, they all have to add up to 180. So I can do 180 minus 164.8 minus the, oops, I lost my sheet. And calculator there, minus 13.7, and that'll give me my last angle of 1.5. So this up here is 1.5 degrees. And then using the law of sines, I know that the sine of 1.5 degrees over its opposite side, which the opposite side is 23.3, has to be equal, and remember I'm trying to find this side here because it's the same as this side over here, is the sine of 13.7 over my y. That was what I assigned that over y. And therefore y is equal to, we're just going to cross multiply and then divide. So this is going to be 23.3 times the sine of 13.7 all over the sine of 1.5. And that's just cross multiplying these two and then dividing by this one. You could do that in a couple of steps if you want to. And then I'm just going to find out what that value is there. So go back to my calculator, and I'm in degrees. Yes, I am. So I'm going to do 23.3 times the sine of 13.7. Enter, and then we're going to divide that by the sine of 1.5. Sine of 1.5. Enter, and I get 210.81. So this is going to be approximately 210.81 feet. So I'm going to go ahead and put that over here, 210.81. I'll go up 2 decimal places to hopefully get close enough. I know that this angle here is 15.2, and I want to find out this height here. So now, for this angle, we want the opposite side, and we know the hypotenuse. So which of the trig functions uses opposite and hypotenuse? And that is sine. So the sine of 15.2 degrees is equal to the opposite over the hypotenuse, to 10.81. And if I just multiply both sides by 210.81, so x is going to be equal to 210.81 times the sine of 15.2. And so I'm just going to take this last value here that I got and multiply that by the sine of 15.2. Sine of 15.2. And I get that the, let me just make sure that's right, 210.81 times the sine of 15.2, and I get that the height of the tower is 55.3, so it's approximately 55.3 feet. All right. If you have any questions, please let me know.